Alright, so we're going to try to factor some polynomials, and this is just a quick review video, so if you've never factored polynomials before, this may not be the right video for you. But if you have done it before and you just need some additional help, a review, so to speak, this might be helpful. So to quickly talk about what we're doing, so we've got factoring and we've got the word polynomials. So let's just look at the word factoring or factor. So if I had the number 20 and I asked you for a factor pair, you could say, 2 times 10 equals 20, 4 times 5 equals 20, and 20 times 1, of course, equals 20. So these are factor pairs of 20. And of course they're commutative, so I could say, rather than just saying, 4 times 5, I could also say 5 times 4, that doesn't really matter. And so that's what I'm doing to this number, is if I wanted you to factor 20, we would say 20 is equal to, or is equivalent to, 4 times 5, or whatever factor pair you wanted. And so when we have a polynomial may be something that looks, like x squared minus 16. So we've got this little binomial thing going on here. The question is there some expression times another expression, or in some cases its own expression, so itself, that would equate or equal the original binomial? So is there something out there, is there something times something else that will equal this x squared minus 16? And indeed there is. We know this is a special case of difference of two squares. And so for the rest of this video, I'll first take you through my thought process and how to approach factoring polynomials, because it's not the easiest thing to do in the world, but it's kind of fun because it's a lot of pattern recognition and almost like puzzle solving. And then basically give you some examples just as a review. Here we go. So here's that process I told you about. This is just kind of something I made up. This is the way I think of it. It's not the only way to approach these problems by any means, or even necessarily the best way, but I first look at every polynomial I'm told to factor and see if I can't take out the greatest common factor. And we'll look into more detail on how, what that would look like for a polynomial. And the greatest common factor, once that's pulled out, I'll look to see if there's any special cases. So is it a difference of two squares? Is it a perfect square trinomial? And if it is, great, I know how to factor it then, and we'll talk about why those are so easy to factor. If it's not, I'll attempt to factor it in two binomials. Now, not every polynomial is easily factored. We haven't in class talked about completing the square or anything like that, so you can factor anything. But at this point where we're at, not everything's easily factorable, and I think that's true across the board. If you've got to do stuff to the equation to make it factorable, it's not necessarily easily factorable. So let's look at some examples. So on this problem, if we're going to follow the process we just went over, the first thing I'm going to do is look for a GCF to factor out. So is there something in common between the coefficients and between the variables that I could pull out? Well, there's really no variable here on the 2, so we're not going to be pulling out an x, because there'd have to be an x in every term to pull that out. But there is a greatest common factor, GCF, between the 18 and 2, which is, of course, 2. So I'm going to start by pulling that out, which was step 1 on that last little chart we looked at, minus 1. And if you're still struggling pulling out the GCF, remember, once you figure out what you're going to pull out, what's the greatest number that will evenly fit into both of your terms, consider, okay, so that's 2. What times 2 is going to get me the first term? Well, 9x squared. And then what times 2 gets me negative 2? Negative 1. So from here, we have to continue, though, and recognize that we can continue to factor this. Now, really, the only time I can think of where we can factor a binomial or which is a polynomial with two terms, so bi meaning 2, is if it's a difference of two squares. So we've got to recognize that 9x squared is a perfect square, because if you were to take the square root of that, you would get 3x. And similarly, 1 is a perfect square, because you know that the square root of 1 is 1. And obviously, we're only interested in the positive versions right now, so I know it's plus or minus 3x or plus or minus 1. We're only interested in the positive versions. And because of that, we know from experience that we can go ahead and factor that, because it is a difference of two squares. So 3x plus 1 times 3x minus 1 should result, if we were to multiply this whole thing out, it should result right back with what we started, which is the idea of a factor. So if you remember the 20, for example, that we looked at, the number 20, if you had said, oh, that factors into 4 and 5, well, 4 and 5 together have to multiply to 20. Otherwise, they're not a complete set of factors. So there are really, you could think of this as being three factors. You've got 2, you've got 3x plus 1, and 3x minus 1 as your three different factors to equal 18x squared minus 2. So the question is, how did I know to go from here to here? Well, there's a pattern in a difference of two squares that's important to note. So let's forget about the 2 for a second. Let's ignore this just for a second, and let's look at the 3x plus 1, 3x minus 1. If you were to multiply those out, watch what happens to the middle term. So I wrote that. So the first one we would multiply, right, would be 9x squared. So 3x times 3x, 9x squared, minus 3x because of the 3x times negative 1, plus 3x minus 1. Well, the way it worked out when we FOILed it is these middle terms have canceled. And so really the only way to get a binomial through the multiplication of two binomials, because check it out, this is a binomial, and it's resulting in a binomial. It's resulting in 9x squared minus 1. The only way to get that is if the middle terms are going to cancel. So you've got to have the same number here and the same number here, but have opposite signs to get those middle terms to cancel. And that's why it only works the difference of two perfect squares. So of course, this right here is my final answer. Okay, this is my final answer. All this stuff down here is I was just kind of explaining and even checking that it would work. All right, let's do a few more examples. So this is an interesting problem because not only is there a GCF to factor out, but it's also not in standard form. So the first thing I'm going to do is write it in standard form just because that's the way I'm used to seeing these. I like them in standard form. It makes it easier for me to think about how to factor it. So I just rearrange the terms. And obviously, there's a greatest common factor of 3 in this case. We can't pull out any of the variables because the 3 on the end, this 3, doesn't have a b to pull out. So we'll say, okay, this is equivalent to 3 times b squared plus 2b plus 1. Now, this is a special case as well. It's not a difference of two squares. A difference of two squares is only a two-term polynomial or a binomial. This is a trinomial with 3 terms, but it's what we call a perfect square trinomial. Because if you were to take the square root of the 1 and multiply that by 2, you'd end up with a middle term's coefficient. So the square root of 1, you know, is 1, and 2 times 1 results in 2. And why does that matter? Why is it significant for a perfect square trinomial in this case? Well, it's significant because if you follow the pattern, or recognize the pattern when you were multiplying these out, you could maybe identify that this is equivalent to b plus 1 squared, and of course we still have that 3 on the outside. And how do I know that? Well, it came from, if you're still struggling with that, perhaps we should go back to the multiplication, because remember we multiplied a lot of stuff like this. I said, okay, we need to multiply this out, and you guys would rewrite this like b plus 1 times b plus 1, because that's what it's equivalent to. And we would get, okay, b squared plus b plus 1, or b squared plus 2b plus 1. And so this is just sort of a recognition that when you square a binomial like this, you're going to end up with this being your first term squared, so that's b squared. Doubling this as your middle term's coefficient, and then squaring this for your last term. And so it's just a simple matter of recognizing this as a perfect square trinomial and going straight to this. And if you need to experiment with it, that's fine. I mean, you could set up, okay, 3, I know I'm going to have a b here, I know I'm going to have a b here, I know the signs of both are going to be 1. What's the only factor pair of 1 that will work? 1 times 1. And then recognizing, oh, that's just, you know, b plus 1 squared. That's fine. If you don't recognize this pattern over here I was talking about, this one right here, just doing it, you know, factoring it the old-fashioned way, setting up what you know and solving for what you don't know, works as well. All right, a few more examples. So this is an interesting one because there's a GCF that we can pull out of 10, so we'll do that. I'm going to start going through these a little bit faster now because I know this video is starting to get a little on the long side. Plus 10n plus 25, so I pulled out factor of 10, and I'm trying to think about this. I think, yeah, this is a perfect square trinomial as well, because I'm thinking, hey, I know I need, you know, if I was to set this up, I know I'm going to have an n here and an n here, and of course my 10 is going to be on the outside. This is going to come straight down. But I know whatever number I'm going to put here and here, when multiplied together have to equal 25, and when added together have to equal 10. The only numbers that do that, the only factors that would do that are the roots of 25, the square root. So 25, or excuse me, 5 times 5 equals 25, and 5 plus 5 equals 10. So when we multiply this out, we get n squared plus 5n plus 5n plus 25, and we have that 10 on the outside still. So this equates to 10 times n squared plus 10n plus 25, and if we were to check it now all the way, that's equivalent to 10n squared plus 100n plus 250, which is of course what we started with. That's me checking it. So this I knew was my answer right here, and all this stuff here I'm putting in blue is my check. Now it'd be cool to write our final answer actually in a more summarized version. It's really 10 times n plus 5 squared. Whoops, squared. Let's see if I can get that written correctly. It looks kind of sloppy. So that's actually, how I would expect you to write your final answer, to recognize that that's n plus 5 squared. Okay, cool. A few more for you. It's funny, the only way to really get good at this is to do a lot. So if you think you got this, feel free to shut this off at any time, those of you who are watching this to get additional practice. But I'm going to go through 2 more examples in case you need it. So if it's, totally up to you. Okay, so in this one, this is interesting. This one right here, there's no GCF to take out because there's nothing in common between 2, 3, and -9 except for 1. So I'm not going to bother pointing out 1 because it won't get me anywhere. So in these situations, I'm going to write down what I know and then try to plug in what I don't know to get an answer. So I know, for example, that I'm going to end up with 2 binomials if this is factorable. This right here, I'm just going to make this 2n, and this is n. It doesn't matter. I could have put the 2n over here, or I could put it here, but I know the only factors of 2 are 2 and 1, so that makes that kind of easy. And then I have to think, okay, my number here is negative, and the number in the middle here is positive. So I know the signs need to be plus, or need to be an addition and a subtraction sign, right? A positive and a negative to get that last term negative. So this is a possibility, or this is a possibility. I don't really know which one it is yet, so I'm going to write both down and know that one of these is going to work. Then I have to think of factors of 9, knowing it's really factors of -9, and that's why I've got a positive number and a negative number in each of these, because a negative and a positive is the only way to get a negative through multiplication. So I started thinking of my factors of 9. So it's really only one choice, right? Or 2 choices, excuse me. You've got 3 times 3 and you've got 9 times 1. Both equate to 9. So the question is which one and which one should get doubled. And if you look at the pattern of multiplication, whatever number goes here with the way I've set this up is going to get doubled by the 2. Because this number is not going to be multiplied by the 2. So let's think. We want to end up with a positive 3 in the middle. So if I made my positive term 3 and the one that gets doubled, and my negative term also 3 but the one that doesn't get doubled, I think this would work, because I can tell you right now that this is going to end up being, let me see if I can draw this, this is going to end up being 6n, positive 6n, and this is going to end up being negative 3n, which result in a positive 3, and then the product of negative 3 and positive 3 equals -9. So I can kind of scratch this out. I've thought this through. I know this is not a possibility up here, but I want to double check what I've written down here. So let me rewrite it first, a little cleaner for us, and then I'm going to FOIL it out, and we'll double check that it works. And I hope that logic there made sense. I kind of basically set up what I knew. I knew there's going to be a 2n and an n. I knew one of the terms was going to be negative and positive, and one of the terms was going to get doubled. And then you just kind of think it through, or even guess and check. Use your eraser if needed. So here, when I FOIL this out, I get 2n squared plus 6n. So 2n squared plus 6n. Negative 3n. And -9 from that. So this simplifies down to 2n squared plus 3n minus 9, which is indeed the original. So this right here, ladies and gentlemen, this right here is the answer. That's the factored version of that trinomial. And anyways, that's pretty much all there is to it when you have a prime non-1 coefficient of the first term here. But you might be asking, what happens if this 2 wasn't a 2? What if it was a 4? Well, then you'd have more possibilities here. You'd have to write out more possibilities besides just, these 2 that I did up top and experiment with it till you find one that worked. I think I've got one more example for you. So this example I've made actually a little easier on us because 5 is prime. So again, we're going to set up what we know. So I know there's going to be a 5x and an x for sure. And this one is actually easier because both terms I know need to be negative. I know they need to be negative because that's the only way to get a negative middle term and a positive end term. Because remember, it's this number times this number to get a positive 9. So they both have to be negative for that. But it's that number. It's these two numbers, one of them being multiplied by 5, when added together equal negative 18. So now I have to think, okay, what are factors of 9 where one of them is going to get, multiplied by 5, and I'm going to end up with negative 18? Well, again, 9 is kind of easy because it's 3 and 3, or 9 and 1. 9 and 1. Whoops. Let's see if I can get this to write correctly. I'm thinking the 3 and the 3 because I know 5 times 3 is 15, and then plus another 3 is 18. So that sounds promising. So let's give it a try. So if I was to fill this in with a 3 and a 3, let's see if this works. Let me get rid of this arrow here. Oops, that's not going to work. It's not going to erase for me. So let's FOIL this out. So I know I'm going to get 5x squared from this. I know I'm going to get negative 15x from that. Negative 3x and positive 9, which is indeed 5x squared minus 18x plus 9. So now I know that right there is my answer. That's my factors of 5x squared minus 18x plus 9. All right, guys, I hope this was helpful. And again, I'll reiterate, this is a review video. So if you've never factored polynomials, this is not the video for you. This is designed for students of mine who, after taking the test, missed 1 or 2 of the problems in this area and just needed a refresher, and they're doing additional practice to hone their skills. If you're brand new at factoring, don't feel discouraged. The only way that I got good at factoring was doing a bunch of them and looking for patterns. There's also some tricks out there like the diamond method and things like that that might be worth Googling or YouTubing. I like to just set up, what I know and think it through. That's my favorite way to solve these. So anyways,